Good morning, class, and welcome to this lesson on Kinematics 10, Properties of Kinematic Graphs. Today we will be able to define the slope and area of different kinematic graphs. So this is going to kind of build upon the last two videos. So if you haven't seen those two, you probably want to go check those out real quick. So let's look at a basic position time graph. Position time graph. We already have established, but I'm just going to review it, that if we take the slope of this line, the slope of the line, the slope is equal to rise over run. The slope is equal to rise over run, and the rise in this example is the y-axis, or the delta x, and the run is the delta t. So what is the formula for x over t? That is velocity. So x over t is equal to the slope. So the slope on a position time graph is equal to the velocity. So this would be a positive velocity, this would be a zero velocity, positive velocity, zero velocity, negative velocity. Okay, so we've already gone over that before, but I just want to review that again. Let's look at a velocity time graph. And a velocity time graph, when it comes especially just to tests in AP world and even in college world, velocity time is probably the most popular because you can go either way with it. So let's look at this one. Let's say we have a velocity time graph where we have a thing accelerating, going constant speed, and then coming back down this way, and so until it finally stops and then turns back around and then starts going back to its original position. Okay, so let's go with that same logic here. If we look at the slope of this line, the slope of this line is going to be equal, let's do it again, slope equals rise over run. The rise is the velocity, or the x or the y-axis, so velocity, the change in velocity, and over the change in time. And so if we look at the slope of a velocity time graph, we are going to get acceleration, because acceleration is the change in v over the change in t. However, on the flip side of that, what if we take the area of this piece? Actually, let's do a simpler piece first, and then we'll go back to it, okay? So let's just take a basic, so we have velocity time, and let's just look at, let's say we just have constant velocity for a certain period of time, okay? So just a straight line going across. If we look at this graph is kind of like a rectangle. It is a rectangle. And there is a certain amount of area under this graph. There is a certain amount of area under this graph. What is this area equal to? What is this area equal to? Well, the area of this shape is equal to the base times the height, right? So the area is equal to the base times the height. Or the area, in this case, is equal to the base time times the height, v, okay? Time times velocity. I'm going to rewrite that as velocity times time. So if you look at this equation, this should kind of look familiar, that velocity times time equals something else. Velocity times time equals displacement. Because if we look at our formula for velocity, delta x over delta t, displacement equals velocity times delta t. So, or this right here. So the area under the curve is equal to displacement. The area under a velocity time graph is equal to the displacement, because and so instead of taking the slope like we did over here, okay, the area is equal to the base times the height, or the v times t, not v divided by t. So if we look at this shape right here, it's the same concept. The area under this curve, both pieces, is going to be equal to the displacement, because displacement equals v times t. And so what would happen here in this situation, this portion would be positive displacement, this portion would be negative displacement. So because basically this thing is traveling away, constant speed, slowing down, stopped, turned around, and now it's coming back towards its original destination. So this would be positive displacement, this would be negative displacement. So our answer to this one would be this, we'll say this is 20 and this is 5. So the answer to this would be 15 because we would take the positive and we minus that negative, okay? Or we minus this portion right here, not minus a negative. That's not going to work. So notice, okay, so let's go back. The slope of a position time graph is velocity. The slope of a velocity time graph is acceleration. The area of a velocity time graph is displacement. And finally, if we go on to acceleration, an acceleration time graph, and I'm just going to, so this thing is positively accelerating, negatively accelerating, positively accelerating, zero acceleration. If we take A times T, or if we take the area of all of these things, okay, if we take the area of all of these things, what is that equal to? That is equal to the average velocity, because velocity is, or excuse me, acceleration is equal to the change in velocity over time. So the change in velocity, or the average velocity, is equal to acceleration times time. So the area under an acceleration time graph is equal to the average velocity. And it's the same thing here where you would have positive numbers, negative numbers, positive numbers, and obviously there's zero because that's just zero right there. So I'm just going to review one more time just to be clear. The slope of a position time graph is velocity. The slope of a velocity time graph is acceleration. The area under a velocity time graph is displacement, and the area under acceleration time graph is velocity. So now you can see how all those are related, and it's very, very common for physics students to be given graphs on test questions because they are indicative of real life things people will measure in order to figure out these different variables.